In this presentation, we shall be discussing the working principle, components of the gas turbine, air filtration system, lubrication, firing system, sprayed, fire protection, water wash, barring, thermal barrier coating, that is TBC, cooling water system, and a startup. Gas turbine works on idealized Brayton cycle, and in gas turbine, if we see the figure on the left hand side, the air is compressed in a compressor from point 1 to 2, and then the fuel is injected in the combustion, the temperature goes up, and that hot gas is fed to the turbine where it rotates the turbine, it does the work, and then the gas is exhausted from the point number 4. If we see the pressure velocity diagram of this process, at point number 1, fresh air is compressed in the compressor, so the pressure increases, the volume decreases, and we reach point 2. From point to 3 is the combustion portion where the gas is added, so at the constant pressure the volume goes up. From 3 to 4 the gas expands in the turbine, and that's how the pressure goes down. If we see the temperature entropy diagram, then at compression, when the air is compressed from 1 to 2, the temperature increases at constant enthalpy, and when the fuel is put inside the combustion, point 2 to 3, both the temperature and entropy increases, and from 3 to 4 the gas is expanded and the temperature drops, and 4 to 1 is actually it is going out. Now, if we see the working principle of the gas turbine, then what happens? The heated fuel is passed through the set of nozzles. The pressure and temperature energy get converted into kinetic energy. The pressure and it passes through the buckets and blade space. The gas expands. Moving plates, buckets convert kinetic energy of the fluid in torque, which results in rotary motion of the wheel. Rotary motion drives generator to generate power or any other equipment, for example compression. Now let us talk about the major components of a gas turbine. So first component is the compressor, then the combustion where the gas is burned, and then the turbine where the gas expands, and then gas goes out. If we see the figure on right hand side, this is the compressor portion, this is the compressor portion, this is the combustion portion, these are the fuel pipes through which the pipe is put, and this is the burner where the fuel is ignited, which expand, and this section is the turbine section from where it is expanding and rotating the turbine. If we see more components of the gas turbine, then there is an air inlet system, then the compressor, then the gas turbine, combustion system, bearings, lubrication system, exhaust system, and a starting device. So in this diagram here we are able to see the starting drive which is required to rotate the turbine and compressor at the designated speed and to give air for the combustion. This is the air intake system from where the air enters. This is the compressor. This is your combustion where the combustion takes place, and this is the turbine and the gas is exhausted. All these are put on a frame, and the oil tank is below the frame for the lubrication system. Turbine and combustion both have got a double casing. So the cooling air flow through the annular, which is the hollow space between the two casing to cool the combustion and turbine casing to protect them from the overheating. All gas turbine use axial compressors, and it gives a very high flow. Now here we will be seeing
The
a
inlet
video
casing
on this
provides a
diesel
smooth
vehicle.
transition flow of air from the filters through the silencers and into the axial compressor. The inlet casing also provides access to the thrust bearing and the inlet journal bearing. Variable inlet guide vanes are located in the inlet casing directly in front of the first row of compressor blades. The vanes are used to regulate the amount of air entering the compressor. The circular operating ring actuates the guide vanes so that all vanes move in unison when opening or closing. Before each set of rotating blades is a set of stationary blades, or blade rings, that direct the air to the next set of rotating blades. The compressor blade rings have stationary airfoil-shaped vanes that direct the air to and from the rotating compressor blades. The rotating blades force the air into progressively smaller spaces as the air passes through the compressor. Heat of compression is generated in the air as it is passed through successive compressor stages. The compressor consists of 16 rows of individually removable rotating blades. Each blade is locked in place by a dovetail arrangement at the base of the blade. The rotor is made up of a bladed compressor spindle and a bladed turbine spindle that is bolted together to make one single shaft.
Now we will be talking about the air inlet system. So in air inlet system there are filters. You can see the filters here. The filter is shown at the bottom right. This is the filter house, and then some places where air temperature is very high, we are using coolers to cool the air to improve the turbine capacity and efficiency. Then there is a duct, there are silencer in the duct to reduce the noise. Inlet air heating manifold in India is rarely used, but it is used in cold companies. There is a trash screen to just stop the bigger materials to come to the filter house, and there is a plenum. It is a duct which directs the air into the inlet bell mouth of the casing. And for cleaning the filter, there is a pulse jet filter cleaning system. The dust that is collected on the cartridge is periodically removed by compressed air pulsing. Pneuma pulse systems use accelerator inducer nozzle in place of venturis, yielding lower initial pressure drop and more efficient cleaning. The operating airflow resistance is comparable to that of conventional three-stage filter system. Coolers are used to reduce inlet temperature to improve GT efficiency and power output. Now we will talk about the airflow. Exhaust air from the exhaust of the axial air compressor goes to the compressor for meeting the combustion requirement. Part of this air is used for other purposes also, like for meeting cooling air requirement for turbine hardwares, for meeting impulse air requirement for air filter, for meeting atomizing a requirement for liquid fuel only, and for meeting purge air requirement before startup and after shutdown. Now we will be seeing some more components of the gas turbine. So on the left hand side we have got a compressor here. This is the combustion. This is the combustion. Turbines have got 6, 8 or 12, 10 combustion as per the size. Fuel comes here and it goes in the combustion and it is getting fired, and then there is a turbine which is either 3-stage or 4-stage. Here these bearings are on the compressor end as well as on the turbine ends, and hand holes and manholes are provided at the bottom of the casing for purpose of maintenance. Cross tube fires, which is shown here, this is the cross tube fire tube. Cross tube fire is used to ignite one burner from another burner, and most of the turbines are, G turbines are using can annular burner, which is shown here. Now here we are able to see a drawing of the burners. So you see in this, all these are the burners, and here there is an opening which where the flame tube or the cross fire tube is provided, because normally it has got only 2 igniters and the flame of other burners ignited from one burner to the another burner through the crossfire tube. This is the spark igniter to start the ignition. This is all fuel nozzle clusters, and this is the actually rotor of the turbine. And here then this is the outlet duct. Now let us see the first nozzle, how the cooling is done. You see all the nozzles, all the buckets and the casing, everything is cooled. So let us see how it is cooled with the air. So you see what we see here, a hot gas is flowing like this, and here cooling air is entering from here. Cooling air is entering from here. There are so many holes. You can see here also there are so many holes in the nozzle. So cooling air comes out from these holes, as well as there is a honeycomb sections, and through that the cooling air goes out from here to keep the nozzles cool. The similar way, the second stage also has got cooling air entering from here. There's a holes here. Through these holes, the cooling air is going out and it is cooling. Normally, the third stage nozzle don't have any cooling arrangement. It is not required. Now, let us see what is shroud. The primary function to provide a cylindrical surface for minimizing the bucket tip clearance and to provide high thermal resistance between hot gases and the comparatively cool shell, and reduce the cooling air by reducing the shell diameter. So you see shrouds are here. Shrouds are here. Shrouds are for the buckets also, and shrouds are for the rotating blades also. So this is the first stage nozzle, and then this is your rotating blade. This is your first stage, second stage nozzle. This is the rotating blade. In third stage, there is no cooling arrangement for the third stage, as we discussed earlier, but it comes after the second stage. So this is third stage nozzle, and this is the third stage bucket, and this is the shroud on the third stage bucket. Now let us talk about how the turbine is getting cooled. In turbine casing, the nozzles, the rotors have a special channeling and holes made through which the cooling air is guided. The turbine casing and the exhaust casing are cooled with air from an motor driven fan or through compressor discharge air. Rotor blades cooling. First and second stage blades are hollow through which the compressed air discharge is passing. Holes are drilled on the tip and the surface of the blade through which the air comes out after the cooling, as we have seen in the previous drawing. Now let us see one more drawing on turbine cooling showing all the stages. So you see here there is a gap, there is a double casing, cooling air is flowing through this casing also. Cooling air is flowing through all the nozzle, first stage, second stage nozzle and bucket, and third stage don't have any cooling air requirement. Now we will be talking about GT stage. So let us see a video on this, that how let us see this video. You see, this is the first row blade and then second row then second row blade, like that. Now let us see. Now we will see how gas turbine gets started. So you see, as we have seen, combustion and gas turbine has governed, cooling air is flowing through the hollows, all these things we have already seen. So you can see one left hand a drawing on the left hand side where the air is coming and going to the combustion, and then the fuel is firing, and after that hot gas is going through that. Now we will show all this in a video form. So this is the compressor, this is your combustion, and these are the turbine rotors, blades. So when the start command is given, this side is actually generator. Now we have given the start command, so the compressor has started rotating and air has started flowing through that. So you see the air is now coming, is passing through the compression, then it will be passing through the combustion. Now now you can see here the air is flowing and it is passing through the compressor. After that the air is now be flowing to the combustion and it will be passing through the, see there is a hollow or narrow space from which it is passing, so that it pulls the combustion, so air is now going, pulling the combustion, and after that air will pass through the turbine. Now we will see the igniter is starting. So you see now the air is flowing through the burner also. Now you see the spark plug has started and now the flame will come. So the fuel has now come and you see now one burner has started, and slowly it with the flame through the crossfire tube will go and ignite all the burners. So you see this is now combustion portion. From here the hot gases will pass through the turbine in turbine section. These are all fuel pipes through which the gas inside and out. See, now all burners are ignited and now the gas is passing through the different stages of the turbine and then it will go to the exhaust. Now let us see what is thermal barrier coating. So you see, thermal barrier coating is actually a coating which is provided for avoiding overheating of the all turbine components which is coming in contact with the hot air. So TBC allows the operating temperature to be increased by 100 to 170 K. Outer, what it has got? Outer layer is zirconium, thickness is limited to 0.25 millimeter. Then there is a metallic bonding layer and then flaking. So due to the transit stresses between the inner and outer surface of ceramic, it may, the TBs may be damaged due and flakes may form which may need repair. Recoating can be always done. Applied in burner and turbine stages, in the burner, in the combustion and turbine stage 1 and 2, blades and vent, transitions is piece and crossfire tube. Now let us talk about turbine auxiliary system. So there is a air inlet system, there is a lube oil system, there is a trip oil system, hydraulic oil system. Startup means automizing air system, inlet guide vane system, fuel gas system, liquid fuel system, compressor wash system, hydrogen gas detection system, shaft supervisory system, fire protection system, and so on. So first let us talk about the turbine lubricating systems. So if we see in the turbine lubricating systems, we have got two filters with I got change all line changeover facility, oil pressure regulator to adjust the oil pressure, oil tank vapor extraction fan, oil purifier or clarifier to clarify the oil when it is dirty, power oil and hydraulic oil systems are, it is taken from lube oil system and the pressure is increased. This is for the safety and operating system of devices. So if we see here, this is the oil tank and in oil tank we have got two pumps, one auto, one standby, and then this is now coming, this one coming through this header and then it is going through the cooler, through the filter, and then it is going to each individual bearing. Now why we do the barring? Let us see, it turns the rotor down to cool uniformly, allowed to avoid wrapping during cool down phases always before a startup. Jacking oil pump, it must be operating during the barring. Barring is always started when rotor is at a standstill. Both motor operated manual barring is normally provided. If barring is interrupted during cooling, then GT must be cooled fully and it should be kept on barring for pre-specified trip mining. Now there is a ratcheting facility provided in the gas turbine. Before starting, GT is put on ratcheting to rotate GT by few degrees to achieve a straightness of the rotor. After GT is tripped or stopped, it will automatically put GT on resetting for few hours to avoid bending of the rotor. So this is all rotor bearing system. Now GTS startup already we have seen. So the sequence is that on giving the start command, the device will start and the compressor valve will open to prevent the compressor to surge. Air will flow up to GT, igniter will start, burner will start, slowly GT will come to 100% steam, a starting device will stop in auto, blow valve will close, and now GT is ready for the loading. Now there is an online compressor water wash system. In that online compressor water system, what happens? Slowly dust deposits on the compressor blades and it reduces the compressor efficiency, compressor output, and as a result, to recover it again, the water wash is done with the detergent and then the losses is recovered. Now, water wash can be done online also when the turbine is running but the gain is less, or if degradation is more, then the turbine is stopped and then the water wash is done and you can see the efficiency here goes up. So here I have already explained the reason that why we do the water wash. Now we will be seeing here a small video which will show us this video will show us how the water wash is done. So let us start.
Everywhere in the air there are particles, tiny particles generated by manufacturing, transportation, and Mother Nature in the form of dust, pollen, salt, and other contaminants. Large quantities of particles or contaminated air make it all the way to the compressor section of a gas turbine. These deposits decrease the airflow and overall performance and efficiency. This raises fuel consumption and global warming pollutants. Keeping the compressor section clean is critical. A clean compressor has shown to reduce fuel consumption, significantly contribute to environmental compliance programs, reduce operational costs, and extend maintenance intervals. The development of the Wood Group GTS highly atomized direct injection system has allowed compressor cleaning to achieve a giant step forward in providing cost-effective and environmentally adapted method.
Now there is a system called cooling and sealing air system. So in this cooling and sealing air system, you see the cooling air, as I described you earlier, is passing through all the hot parts of the turbine and it is cooling the system. Now there each gas turbine has got a system called hazardous gas system. This is all accessories and turbine compartments have got hazardous gas detector. Normally 2 are mounted in accessory compartments, 4 in turbine compartments. In case of any fuel leakage, this is a pre-alarm to take any preventive action. In case of fire, fire suppression will trip the G2 and CAT gas will release to suppress the fire. So system which will be well protected from fire of C2 system, turbine protection, generator protection. Turbine compartment have 2 banks of cylinders. One bank will like an instant release while the other will be extended release. For UV detectors are there for this purpose, and Now let us see what all we need to monitor. We need to monitor the pressure at different places. We need to monitor temperature, speed. We need to monitor the flame. We need to monitor fire detection system, shaft voltage and current, trip systems, servo valve interface, vibrations and operating interface, startup, shutdown and data logging and trending. Scene check and synchronizing for generator only. Now let us see what is a spread. Most spread problem is found mostly in the liquid fuel system, and the spread is actually the maximum difference between the average value of all TET turbine exhaust temperature and one having maximum deviation from the average value. High spread will provide unequal circumferential expansion of the gas turbine. It may damage the turbine. It will develop a stress within the gas turbine. Unequal fuel flow from different burners cause more spread. GT will first reduce the load to the control spread. If value is still high, GT will trip on high spread. This is caused by unequal fuel firing, mostly liquid fuel. Recleaning of oil gun will resolve the problem. And what is a spread? A spread is the maximum difference between the total of all turbine exhaust temperature divided by number of burners and a particular TT. So thank you very much for having a patient hearing. I have given you the link for all the videos which I have uploaded on the YouTube. Please press like and subscribe my channel to get information about new video uploaded in the future. To get more than 100 slide PDF of this presentation, please send me a email given on this slide. Thank you very much.